I'm Predrag, today's host of this webinar. Thank you for joining the Entropy webinar entitled Delay-Doppler Domain Communications for Future Wireless Networks. I hope you can see presentation. If someone can just confirm if you can see the presentation. Okay, great. At the beginning, I will just share some information from our side to introduce all of participants with MDPI. MDPI is a pioneer in scholarly open access publishing, and we supported academic communities since 1996. We are based in Basel, Switzerland, and our mission is to foster open scientific exchange in all forms across all disciplines. Our 468 diverse and open access journal include 459 peer-reviewed journals and 9 conference journals, are supported by more than 295,000 of academic experts who share our mission, values, and commitment to providing high-quality service for all of our authors. This webinar is organized by Entropy Journal. Entropy is an international and interdisciplinary peer-reviewed open access journal of entropy and information studies, published monthly online by MDPI. Today's program is that our chair, Dr. Professor Shuanggyang Li, will start with introduction. After that, we will have 2 presentations of Professor Fan Liu and Professor Stefano Buzzi. And after each presentation, we will have a question and answer session. At the end, Professor Dr. Shuanggyang Li will close this webinar. More information about this webinar is that we want to add that if you are interested in submitting your research to a special issue that is linked to this topic, the special issue is Delay-Doppler Domain Communications for Future Wireless Networks, 2nd edition. Guest editors are Chair Dr. Shuanggyang Li, Dr. Qin Tao, Dr. Baoming Bai, and Dr. Han Yu. Deadline for this special issue for receiving manuscript in this special issue is 15 August. More information you can find on our website. Also, some technical information before we start. If you have any questions for our speakers during this webinar, please post them in the Q&A box at the bottom of your screen anytime during the webinar. And please also remember to add the name of the person to whom you are addressing your questions. And the last information before we start with the webinar is that as the participant of the webinar, you will be able to download an electronic certificate of attendance by accessing our cforum.net after the webinar. Now I will give the word to Dr. Shuanggyang Li, and we can start with this webinar. Thank you.
Sure. Yeah, thank you for the nice introduction. I think you have pretty much covered everything I want to talk about. It's also a great honor for me to be here to host this presentations, and we are very glad to have Professor Fan Liu from China and Professor Stefano Buzzi from Italy to share their recent research progress on the topic of Delay-Doppler communication and particularly for sensing. So as project has mentioned that if you have any questions, you can put in the Q&A session, or you can send me a direct message at the end of each presentation. We'll have a Q&A sessions. Okay, so I think without further ado, please join me to welcome our first speaker, Professor Fan Liu from Southeast University of China. Thank you.
Okay, so many thanks for the organizer to invite me to give this webinar on our recent research progress on sensing with random communication signals. And I'm Fan Liu from Southeast University. So this is a series of works that has been collaborated with many of my distinguished colleagues, and including Dr. Shuanggyang Li here. Okay, so let me first introduce the outline of my talk. So I will first talk about some background and motivation, and then the first part of the main results, and then some numerical simulations, and then the second part, which is on continuous ISAC signaling, and then the numerical simulation, and finally I will deliver some concluding remarks. Okay, so for the background, I think I will not spend too much time on this. I think everyone here should may know the concept of ISAC, so integrated sensing and communication. So basically, it is a design paradigm and a corresponding enabling technology where sensing communication systems are integrated to efficiently utilize resources and even to pursue mutual benefits. And so basically, ISAC was recently recognized by the ITU, International Telecommunication Union, as one of the 6K usage scenarios for 6G. So it is officially a 6G technology now. Okay, so if we look at the ISAC transmission from the perspective of our current cellular networks, we have to reuse the current cellular networks and corresponding communication signals to do sensing. The natural choice is to build upon our sensing capability over the 5G NR protocols. So if you look at 5G NR current, which is in the progress of the 5G Advanced. So if you look at 5G Advanced, there's already some basic protocols on ISAC. So this kind of 5G Advanced ISAC transmission, they basically exploit the phasic layers reference signals, which are also known as pilot signals. These are including CSI reference signals, demodulation reference signals, phase tracking reference signals, and others. So basically, if you look at the 5G transmission, they are exploiting physical layer reference signal, or even worse, they may just simply use 10% of the resources to transmit radar signals like chirp signals. So this kind of technique, they are very easy to be implemented, but they're far from optimal since the reference signals, they occupy only 10 to 15% of the time frequency resources, because most of the resources has to be, as we know, allocated to data transmission. So the data payload, which occupies more than 85% of the resources, needs to be fully exploited to improve the sensing resolution and accuracy. So for example, here you can look at some basic frame structures of the 5G NR frames. So this kind of colored blocks, they are different physical layer reference signals, and the most of the resources, as you can see, they are located to the data payloads. But these data payloads, they are not exploited in the current 5G NR 5G advanced ISAC transmission. Okay, so then if we are going to reuse the data payload to do sensing, then we have to look at a major difference between the communication data signals and the radar, conventional radar signals, or the conventional pilot signals. So that is, if you look at the radar system, they typically employ well-designed deterministic signals for target sensing, for example, chirp signals or phase-coded sequences with good ambiguity properties. They are all well-structured, well-designed deterministic signals. But in order to convey information, the communication data signals have to be random. For example, if you look at the Gaussian channel, we know that the Gaussian constellations or Gaussian codebook will achieve the capacity of Gaussian channels. So communication data signals have to be random. And if you have more degrees of randomness, then you will have more capabilities to convey information. So basically, sensing with random signals will lead to performance degradation. Actually, if we look at the information theory, we know that the sensing optimal constellation has to be a constant modulus constellation like a PSK. Okay, so then you will lose the degrees of freedom in the amplitudes. So but if you're going to exploit that degrees of freedom, then there must lead to the performance degradation. So that has already been proved in our recent publications. So that is the basic motivation. So if we are going to do sensing using these random signals, we'll have to answer the fundamental question. So how to characterize the performance of sensing using random communication signals, okay? Now let's look at the ISAC waveform design methodologies. So as we all know that in ISAC there are three major design methodologies. One is sensor-centric design, which is to embed information in the legacy radar waveforms. So it has negligible impact on the sensing performance, but it generally leads to low spectral efficiency and even worse, the incompatibility with our current cellular networks. Because in our 5G protocols, we will not use radar waveforms to do communication, right? So another primary design methodology is sensing communication-centric design, which is to sensing with standardized communication waveforms. So it has negligible impact on the communication performance and is fully compatible with cellular networks. But it may lead to the sensing performance degradation due to random data payload signals, just like I discussed here. And there's another category which is known as joint design, which is to conceive novel waveform based on nonlinear optimization techniques. And it can achieve a scalable sensing communication trade-off, but it is very difficult to be implemented in communications in practical systems. So we anticipated that in our future 6G networks, communication-centric design will be the most promising, methodology to implement ISAC due to its, compatibility with cellular networks. Now, here comes a key question here. If we're going to adopt communication-centric design, then which communication waveform has the optimal sensing performance? So that is a very fundamental question that we have to answer here. To answer that question, we should first look at what is a communication waveform. So now let's start with the very basic building block, which is a constellation in a communication system. So if suppose that we're going to transmit n constellation symbols, so S1 to Sn. So these random symbols, they are independently and identically distributed subject to some constellation S. So it has some properties here. So we normalize its power, so its variance is equal to 1. And it has 0 mean, so and it also has a 0 pseudo variance. So so we should pay attention here, because here you can see the square is directly imposed on S, but here the square is imposed on the absolute value of S, right? So they are different. So this one is called a pseudo variance, okay? Because it is not a real variance. So we need its mean and the pseudo variance to be 0. So most of the constellations satisfy these properties. For example, PSK and QUAM and APSK and many others, okay? They satisfy these generic conditions. And another very important parameter of the constellation is the so-called kurtosis. It is defined like this. So under the above assumptions, the kurtosis is nothing but the expectation of the fourth power of squared S. So it is basically the fourth moment of the constellation. Okay, so kurtosis is very important, and we shall see the reason why in our later discussion. So if we look at the Gaussian constellation, so for example, if this S follows 0 mean and a unit of variance circularly symmetric normal distribution, then it has a kurtosis of 2, which is exactly a baseline that we will adopt in our definition of different constellations. So based on this Gaussian constellation kurtosis, we could basically divide all the constellations into two categories. One is sub-Gaussian constellation, which has kurtosis less than 2. For example, QUOM and PSK, and we have a table here with their kurtosis. And so PSK definitely has a kurtosis of 1. And all the other QUOM constellations, you can see, they have a kurtosis between, let's see, 1.3 and 1.4, okay? There are also super Gaussian constellation, which is that when the kurtosis is greater than 2, for example, index modulation. So because in index modulation, we may always, transmit 0 also as a constellation symbol, then the kurtosis may be greater than 2. And then also for the PSK, for the APSK, with drastically varying amplitudes. For example, imagine that you have a 16-4 APSK with 4 circles, but each circle has a radius that is exponentially growing. Then you will end up with super Gaussian APSK constellation. But not all APSK is like this, just some specifically designed APSK, okay? So we have two categories of constellations, and we shall see they're very important in our later discussion. And what is a communication waveform? So in our classical communication theory, communication waveform is nothing but a modulation basis. So it is orthonormal signaling basis carrying random symbols, and which can be modeled as a unitary matrix here to apply to this size n random symbols. So each of these U vector is an orthonormal basis, right? So here are some typical examples. For single carrier waveform, U is nothing but identity matrix, because in that case, we are transmitting these symbols in the time domain consecutively. So note that this X is in the time domain, okay? And if U is IDFT matrix, so Fn is the normalized DFT matrix, and with the Hermitian, this is IDFT, right? So if U is IDFT, then this is what we know the OFDM, right? So where in this case, we're placing the symbols in the frequency domain. And if U is the Hadamard matrix, this is the CDMA 2000. And so if U is like this, which is a Kronecker product between IDFT and identity matrix, then this is the famous OTFS. So in this case, the symbols are placed in the delay-Doppler domain, which is our today's thing, right? And recently there is another waveform called AFDM, affine frequency division multiplexing, which has a modulation basis like this. You have an IDFT matrix in between two diagonal matrices, okay? And this diagonal matrix actually forms the basis of chirp signals. So in AFDM, you are simply using orthogonal chirp signaling basis to convey, symbols. Then here is a key question here: which modulation basis has the optimal sensing performance? So this is a very fundamental problem that we have to answer here. And note that in this model, we assume Nyquist sampling. Okay, so we will discuss the oversampling cases in our next part of the talk. Now, to evaluate the sensing performance, we consider the ranging tasks. So ranging means that we need to estimate the distances of multiple targets. And in such a task, we usually use autocorrelation function, ACF, as a performance indicator. So the ACF is actually a self-convolution of the signal X. And it has different categories. One is a periodic ACF. So that means this X, periodically convolve with itself. In that case, this is for signals with cyclic prefix, so with CP. And its discrete form is like this. So this R tilde K means the periodic ACF. And here, this J tilde K is a periodic time shifting matrix. So you can see it contains two identity matrices in off-diagonal entries here, right? And with that, so imagine that you multiply this J tilde K to X, then you are simply copy the tail or k elements of the x to the beginning, right? So that is essentially a periodic time shift, and then you multiply that with x. You can calculate the inner product. Then that will produce the kth point on the ACF. And also there's another ACF, which is aperiodic ACF, right? So this is for signals without CPU, which simply removes this identity matrix here. So this is replaced by a zero matrix. Okay, so what is the performance metric? We usually use the saddle level of the ACF to measure the ranging performance. So imagine that you have a very bad ACF, then you may end up with very high saddle lobe, and this high saddle lobe will mask the main lobe of some weak targets. In that case, you will have very poor detection probability when you do multi-target ranging, right? So we will have to minimize the saddle lobe level. So what is the saddle lobe in this case? So if you can see, if we let k equals to 0, then these two matrices, they are becoming identity matrix. And then this represents the mean lobe, which is essentially the energy of the x. And if k is not 0, then that is a saddle lobe, right? So here we define saddle lobe as the square of rk or r tilde k. So this is for the AASF and the PASF case. So why we impose a square here? Because this RK and R tilde K, they are complex function. So we impose a square here to measure their saddle lobe, which becomes a real number in this case. And note that here, due to the randomness of the ISAC signal, so here X is random. Why is that? Because S is random. So they are random communication symbols. So we'll impose expectation on the saddle lobe level. So we just put expectation over this square of RK, and we shall investigate the statistical property of the ACF rather than a specific realization, because the ISAC signal is random in that case. So we put an expectation here, okay? Then if you expand this RK, you will end up with this kind of expression. Now, the problem is very, clear here. So what is the optimal modulation basis, or what is the optimal communication waveform for ranging? Here we just wish to minimize the expectation of the summation of saddle lobe level. So here, this is called the integrated saddle lobe level, ISL. So the saddle lobe added up from 1 to n-1, right? And with the expectation here. So you can see when minimize a stochastic function, right? So expectation of a random variable and over the unitary group, because U is a unitary matrix. So this is basically a non-convex stochastic optimization problem, which is highly challenging to attend an analytical solution. So our main contribution is that we derive the closed form solution of this problem and prove that the IDFT matrix is an optimal solution for sub-Gaussian constellation. And especially if we look at the PACF and AASF case, we are able to prove that OFDM, so which is when U equal to IDFT, is the unique globally optimal ranging waveform for QUAM and PSK constellation in the PACF case, and is locally optimal in the AACF case. Okay, so these are the physical insights of our results. So let's look at the details, how we arrive this main results. So we could basically derive the closed form of the EISL in PACF and AACF cases. So these derivations, they are very challenging, but we are still able to get the closed form with some special tricks. So you can see that here we have n multiplied to n-1, which is a constant number. And here this mu4 is the kurtosis of the constellation that I just mentioned here. So this is mu4. And here we have the alpha fourth power of the alpha norm of Fnu. So remember, Fn is a DFT matrix. U is our waveform, which is the modulation basis. Okay. So here, if we are going to minimize this guy, minimize the EISL, we have to look at the sign of mu4 minus 2, okay? So very, coincidentally, 2, as we know that 2 is the kurtosis of Gaussian cancellation, right? So for sub-Gaussian cancellation, we have mu4 less than 2. Then if we're going to minimize this summation, we're essentially maximizing the fourth power of this alpha norm, which end up with this problem, okay? So this is a very interesting result because this stochastic optimization seems to be very challenging, but we can equivalently transform it into a deterministic maximization problem like this. And what's even interesting that we can prove that the global maximizer of this problem is U equals to IDFT up to column permutation or phase shifts. All of these are OFDM waveforms, okay? So you can see if we multiply this IDFT to DFT, then inside the alpha norm, we get an identity matrix, and we know that the fourth power of identity matrix of the alpha norm is maximized, is the maximum, okay? And in that case, we could also prove that OFDM is the globally optimal waveform that minimizes not only the EISL, so the summation, but also the individual settler level. So for each of this term, we can also prove that OFDM achieves the minimum settler. And there's also a corollary here. So single carrier is the only waveform that achieves the lowest Doppler settler level for sub-Gaussian cancellation, which is a duality because single carrier for Doppler is like OFDM for delay, okay? So there's a duality between them. Okay, so this is the results for the super Gaussian cancellation. So if we have a cancellation kurtosis greater than 2, we have to minimize this alpha norm, fourth power of the alpha norm like this. So this problem, the global minimizer is nothing but U equals to identity matrix up to column permutation or phase shifts. So all of these are single carrier phase frequency domain equalization waveforms. So SC with CP basically. And basically we could see that all the super Gaussian cancellation achieve the same expectation of ISL on the single carrier waveforms, but their mean lobe levels depend on the cancellation kurtosis. You can see that if you have greater kurtosis, you will end up with higher mean lobe. But since this has a, this is multiplied to n, but here you have n square, so the contribution of the kurtosis can be basically, omitted if n is sufficiently large. So this is the results for super Gaussian cancellation. And what about AAF? So for AACF, we can also derive the closure forms of the EISL, which is a little bit different from this guy, right? As you can see, we have n multiplied to n minus 1 over 2. And again, we have mu4 minus 2 here. But here we have the fourth power of alpha norm of f2n tilde, multiplied to u. So what is this matrix? So this f tilde is a 2n by n matrix. It contains the first n column of the size 2n DFT matrix. So it is not a square matrix. Then if we adopt the same technique, if we're going to maximize this alpha norm, we are no longer able to prove that IDFT is the global maximizer. We can only prove that IDFT or OFDM is a local maximizer of this problem. So, but the simulation results show that there's no other waveform without a CP achieves a lower settler level than that of the OFDM, despite that its global optimality is not guaranteed. Okay, so why is that? Because maximizing the alpha norm here over the unitary group for an arbitrary matrix Z generally remains an open problem, even in the optimization theory. Okay, so this is a result for AACF and sub-Gaussian cancellation. And for super Gaussian, the conclusion is the same with the PACF. So global minimizer is identity matrix. So single carrier is the optimal for super Gaussian cancellations. So now we have some let me see how much time to our left. Okay, so now we have the mathematical results for the optimal waveform, optimal modulation basis. So we wish to know what is the physical picture behind these results. We have to know the physical interpretation of the main results. Here is a possible physical interpretation. So if we look at the ideal case that we have a completely flight spectrum like this, right? We know that in the time domain we'll end up with a delta function, right? Like this. Okay, so this is the Fourier duality between frequency and time. Now, because we are now using a random waveform, we have some random symbols in our signal, then that will incur random fluctuation in the frequency domain like this, right? Then we will not have an ideal delta, but we will end up with some side lobes in the time domain, right? So then we can see that basically the flatness of the amplitude spectrum, which is proportional to the frequency domain kurtosis. So how can we measure this, flatness? We use the, frequency domain kurtosis, which you can imagine it is like a variance of the squared spectrum. Okay, so it's the fourth moment. So if we look at the frequency domain kurtosis, its value will measure the flatness of the spectrum. But how about our communication waveform? If we apply a unitary transformation over S, what we do is that we performing unitary transform over IID symbol sequences. It will make it approaching Gaussian according to the central limit theorem, right? So this is the basic theorem in probability theory. So consequently, unitary transform will increase the kurtosis of the sub-Gaussian symbols, but decrease the kurtosis of super-Gaussian symbols. They are approaching Gaussian constellations from two different directions. One is increasing and one is decreasing. So these are two different type of constellations. So now we wish to know what waveform has the lowest delay set lobe. Then that is to ask what kind of unitary transform will achieve the smallest frequency domain kurtosis. So you can see that the frequency domain of the signal is like this. We apply a DFT to X, we end up with FNUS. So S is our IID symbols, right? So we would like to know, what kind of U will minimize the frequency domain kurtosis, right? Like this. So the answer is very simple for sub-Gaussian because any unitary transform, so FNU is again a unitary transform. Any unitary transform will increase the kurtosis of sub-Gaussian. Then the best strategy is to keep, the sub-Gaussian constellations as is, right? Then you can see this U has to be an IDFT matrix. Then FNU is identity matrix, which left S as they were. Okay, so in this case, OFDM is optimal for sub-Gaussian. But how about super Gaussian? So for super Gaussian, we know that any unitary transform will reduce its kurtosis. So we need some unitary transform that reduce the kurtosis to the most. Then this U has to be an identity matrix because in that case, FNU is DFT, which just rotates our symbol from the time domain to the frequency domain. Then you can see in that case, we'll end up with the maximum rotation in the unitary transform. Then in this case, U has to be identity matrix, which means single carrier waveform is the optimal for super Gaussian constellations. So here, these are some physical interpretation. I hope it is helpful to your understanding of the results. And here are some numerical results. We compare single carrier CDMA OFDM, 3 waveforms, and with different constellations. So 16 QAM, 64 QAM, and a specifically designed super Gaussian 64 APSK constellation. So you can see for QAM constellations, we have, OFDM has the lowest set lobe level everywhere among different waveforms. And here, this is for the AACF. But for super Gaussian, you can see OFDM is the worst, but single carrier is the best. Okay, so some other results, if you can compare the actual ranging performance for different waveforms, different constellations, you can see that OFDM always achieves the best ranging performance among these three waveforms. Okay, so here are some concrete ranging results. Okay, now I will also elaborate on the second part, which is the continuous signaling. So as you can see in our previous signal model, we use orthonormal signaling basis to carry discrete symbols, but this X is still discrete. This is Nyquist sampling, as we know, right? So here is a key observation. Nyquist sampling is sufficient for communication because if we impose Nyquist, post shaping, then we can remove the remove the intersymbol interference, right? And if we sample at the integer multiple of each, symbols, then we can completely get this, discrete symbols without, interference. But this may not fully capture the sensing performance because the sensing performance is basically determined by the continuous signaling, right? If we look at the ambiguity function, the autocorrelation function, we should look at the whole picture, which is the continuous ambiguity function, continuous, ACF, because there are always targets that they lie in between symbols. So if you only sample the integer multiple of symbols, you will miss those targets. Okay, so that is the motivation for us to consider the continuous, signaling, in which case we need Nyquist pulse shaping. So this is the basic assumption for Nyquist pulse shaping. Still, we have this X. Okay, so these are time domain symbols, and they are convolved with a pulse, which is PD here. So this Nyquist pulse has some properties. So first of all, it's autocorrelation function, which is like this, has this kind of property. So basically, so if you sample this autocorrelation function at the integer multiple of the time of the symbol duration t, then it is 1 only when n equals to 0, and it is 0 and n is not 0. So this is basically the zero intersymbol interference criterion or Nyquist criterion in the time domain. And it can be translated to a frequency domain criterion, which is called a folded spectrum. So here, this GF is the Fourier transform of the autocorrelation function, and basically it is the power spectrum of this pulse. Okay, so that means the folded spectrum means that if you put our the power spectrum of this pulse, you copy many of this spectrum in the frequency domain, and with a period of let's see 1/t, then you can see that if they added together, they have to be a completely flat spectrum like this. Okay, so that means basically this row-off factor, this row-off part of the power spectrum should added together with the left part, right, and then end up with a flat a constant number like this. So these two row-off parts, they will sum up to a constant. So that is the basic folded spectrum or frequency domain like Nyquist criterion, which is equivalent to this time domain criterion. Now, let's look at how to model our ISAC signal for this, pulse shaping signals. So we do an oversampling of the ISAC signal, which means that for every symbol, we sample, we sample L, subsamples over every symbol. So that means we have a sampling time of Ts, or we have a sampling frequency of 1/Ts, okay? So this is the oversampling ratio L, and it should be larger than 1, because if it is equal to 1, then this is Nyquist sampling like we have already investigated before. So with this oversampling ratio, we can, write down the whole model like this, right? We have this xn convolved to some delta function, and then convolved to so this is a circular convolution. because of the addition of CP, convolve to the pulse, okay, like this. And we can, formulate a compact expression of the pulse shift ISAC signal, which is to multiply the upsampling signal with, circulant matrix formulated by the pulse, the value of the pulse, like this. So this X up, as you can see, we insert, so every symbol, symbol we will insert, L minus 1 zeros in between two symbols, like this. And then this is X up, and then this P matrix is a circulant matrix formulated by the pulse, like this, okay? Then we can again use the expectation of the squared PACF, which is defined like this. So this we have a X tilde Hermitian multiplied to G tilde K. So here J tilde K is again a periodic time shifting matrix, and then multiply to X tilde again, and we consider the expectation of a square as the Z lobe, okay? And then what we have done is that we characterize the PACF of the pulse shift signal, right? And characterize its statistical probability by deriving the expectation of the squared RK like this. And it turns out that this expectation has a very, very interesting structure, which is called iceberg in C structure. And I will show you the results later. So basically, you can decompose this square of the expectation of the square into the square of the absolute value of this expectation plus the variance of RK. So this is based on the definition of variance, and this is exactly the average squared average of this RK. And here this is the variance of RK. And here, this V tilde matrix is determined by the waveform. Okay, is determined by the waveform here. So this V is U Hermitian F IDFT, and here V tilde is V element-wise product with V conjugation. And here, this Fk plus 1 contains the first n entries of the some columns of the DFT matrix. And here, this G is determined by the pulse. Okay, it's basically the squared spectrum of the pulse. So you can see that we have all the building blocks of a communication signal. We have the cancellation, which is reflected here in the kurtosis. We have the pulse shaping, which is here in GK, and then we have the modulation or waveform, which is here in V tilde. Okay, so this is a universal equation to characterize the ACF of any communication waveform. And in addition to that, so we will show you the structure of this guy later. But in addition to that, we will also need to discuss the coherent integration of the random signaling signal sensing. So when targets remain stationary across, let's see, M transmission slots, then we can improve the sensing performance by randomly realizing MID symbol sequences S1 to SM from certain constellation and averaging over their corresponding matched filtering outputs. Then the corresponding PACF becomes like this. Okay, so you have a 1 over M with a summation of MID ACF like this. Okay, so in that case, what it will be, so we use a bar here to differentiate between the non-integrated RK and the coherent integrated RK like this. So we can also calculate the expectation of this square of the bar RK, and it turns out that still it has the mean part and the variance part, but the variance part will be reduced by M times due to the addition of MID transmission slots. Okay. Now let's look at why we call this structure iceberg in the C structure. So this is a very simple example with a single carrier waveform, 16 QAM, and root raster cosine pulse shaping. So you can see that this part, which we call iceberg, is basically exactly the square the ACF of the pulse itself, okay? So it's the ACF of the pulse itself. And it forms the basic geometry of the whole ACF. And this part, sea level, is here, okay? And here. So you can see that this is determined by the data, the random data, the variance of the random data. And if you consider, for example, 100 coherent integration of 100 transmission slots, then you can effectively reduce this sea level part by 100 times, or 20 dB in this case, okay? Then that will expose more of the iceberg, will expose more of the autocorrelation function of the pulse itself, right? So it's like this. So you can see that this iceberg part represents the deterministic part of the signal, which is determined by the pulse. And this sea level part represents the random component in the signal, which is mainly determined by the random data symbols. Okay, so if you do coherent integration, then you can reduce the randomness of the data, due to the law of large number, for example, and then that will expose more of the deterministic part of the signal. Then that will expose more of the iceberg. Okay, so this is the iceberg in the C structure, and so with the coherent integration, you can reduce the sea level part, but still you will then in that case the performance in this region were determined by the iceberg. So that will inspire us to design some pulse for that is good for sensing. Okay, then what about the optimal waveform in this case? So we can still prove that OFDM and single carrier, they are optimal for sub-Gaussian and super Gaussian cancellation respectively. And the proof is a little bit different from the previous cases. Here, because we have a pulse here, and we shall prove that for arbitrary Nyquist pulse shaping, we are able to minimize the sub-Gaussian, the set lobe of sub-Gaussian using OFDM, and for super Gaussian, we minimize the set lobe using single carrier. And more of the details you can look at our recent technical publications. Now we have this iceberg in the C structure. So this structure inspires us that if we have a sufficient number of coherent integration, so with a sufficiently large M, you can see if this M is sufficiently large, then the sensing performance will depend mainly on the geometry of the iceberg, because the randomness of the data can be reduced to the minimum in that case. Then that inspires us that we can design some Nyquist pulse that, for example, reduce the set lobe of some specified delay region in this case, right? So for example, here we can consider two different objective function to design this pulse shaping. So this technique we call iceberg shaping. So basically, we can consider integrated set lobe level. So for example, we're interested in the target inside this set lobe region. Then we minimize the summation of all the set lobe level within this region, okay? Or we can minimize the maximum of the set lobe within this region, right? So these are two different objective functions. And then with that, we will need to design this G tilde K, right? So this is the spectrum of the pulse. We'll needed to, satisfy the, for example, the here the Nyquist, criterion, which is a folded spectrum criterion. So we have this, row of constraints, and we also have the monotonic spectrum and power constraints. So with these constraints, we minimize the, objective function of either this one or this one, and then we end up with some very good results. So here is the numerical results for this continuous signaling. And so here we use RRC pulses, okay, with 0.35 row factor. So the impact of the modulation basis, as you can see, OFDM is always, the optimal for sub-Gaussian. And if you consider coherent integration for 100 times, you can reduce this sea level part by 20 dB like this, okay, for either single carrier or OFDM. And what about the pulse shaping? So this is iceberg shaping. So for example, we're interested in some targets within this region. Then we can minimize the integrated saddle lobe level within this region. And you can see that, so this is our designed pulse. And here, this is the RC pulse. And you can always reduce your C level to this level by coherent integration. And after that, you will see that we can have a comparison here that the RC saddle within this region is like nearly 30 dB higher than the design pulse. So that means we will end up with huge gain over the RC if we would like to detect some weak targets within this region. Okay, and this is spectrum of the two pulses. So here are some ranging performance. Okay, so you can see for PSK here, we compare OFDM and the single carrier. We have, the OFDM is always, better than single carrier, and our design pulse is, has for example, more than 60% improvement in terms of single carrier and even more for OFDM compared to RC. Okay. And here is for COM. Again, you can see that design the pulse without integration, coherent integration, you can see both pulses, they perform very bad. But with coherent integration, for example, 1000, then we will end up with a huge, performance improvement compared to the non-coherent, no integration cases. Okay, and in particular, the design pulse still have like 50% improvement compared to the RC, the root rest cosine. Okay. Okay, so here are some take-home message. So that's pretty much of my talk. And the main contribution of my talk includes that we derived the closed form of the average saddle level for random ISAC signals under arbitrary modulation basis, constellation mapping, and Nyquist pulse shaping. And we proved that OFDM or single carrier achieves the lowest average ranging or Doppler saddle level for COM and PSK. And we proved that the coherent integration reduced the randomness, reduced the C level of the autocorrelation function, and the ranging performance can be improved through our dedicatedly designed iceberg shaping technique. So here are some practical design insights. For ISAC system using orthogonal modulation, COM PSK constellation, and matched filtering algorithms, OFDM is the optimal ranging waveform. Okay, so no need to design new waveforms in this case. Here there's here the basic assumption is that we are using random IID symbols to do ranging, not pilots. So if we consider pilots, then this can be different. So if we consider IID random symbols, OFDM is optimal for ranging. Okay, no need to design new waveforms. And the saddle lobe generated from random data may be significantly reduced by coherent integration. And the pulse shaping design plays a vital role in communication-centric ISAC. Okay, so if you're interested in all the technical details, you can look at our recent publications and basically these two papers. Okay, so this paper we propose this iceberg in the C structure, and here this paper we prove the optimality of OFDM. Okay, so thanks for listening, and I'm open for questions.
Thank you for Professor Liu of this great presentation. We have received several questions, and I hope you have time to answer it. Okay, so since our main topic actually for today's seminar is about OTFS, and you here prove a lot of different properties of different waveforms. So the question will be, what do you think OFDM or other, for example, AFDM new waveforms will play a role in the random ISAC signaling?
Okay, so that is a very good question, basically. So if we look at OFDM, and so here, let's look at the results here. So here we prove that OFDM let's only consider sub-Gaussian constellation, which is the commonly used constellation in our current cellular networks. So for OFDM, we know that it achieves the lowest set lobe for ranging, but unfortunately, it will result in the highest set lobe for Doppler. But single carrier is the opposite. So it has the lowest set lobe for Doppler, but highest set lobe in the delay or in ranging. Okay. So in that case, you can see OFDM and single carrier, they represent two extreme points. So one is good for ranging, but the worst for Doppler, and the other one is optimal for Doppler, but is the worst for for ranging. So OTFS and AFDM, I believe they may play a role in the trade-off between these two waveforms, because essentially these two waveforms, OFDM and AFDM, and particularly AFDM, I think, they are defined over some region that is, in between time, time domain and frequency domain, right? So, from an intuitive thinking, then this AFDM should be able to achieve the trade-off between delay and Doppler. So I think in that sense, they play a very important role in the design. Yeah.
Thank you for the answers. We just have received a new question from the audience saying, have we ever compared, for example, using random SIG signaling, comparing with deterministic signals with OFDM, for example, ZC sequence with OFDM?
Okay, so I presume that the audience is asking Zadov-2 sequence, right?
Zadov-2. I think it's Zadov-2. Yes.
Okay. Okay. So we actually has this comparison in our recent project. Basically, we consider 5G uplink sensing using sounding reference signal. So sounding reference signal SRS is exactly Zadov-2 sequence. And basically we have so this SRS, they have different patterns. So they may have a frequency hopping mode that you can occupy part of the subcarrier within one symbol, and then another part of subcarrier within the other symbol. So basically, if you look at the frequency hopping mode of the SRS or ZC sequences, then unless it occupies the whole bandwidth using this frequency hopping technique, then it will give you, the very low set lobe and exactly the same mean lobe with the case that you're using all the random data. Okay. But if it only occupy part of the subcarriers, it will has a very poor performance in that case.
I see.
Yeah. Yeah, and another gain that we can mention here is that if you consider sensing with the data, it will provide a huge ISNR gain, not only the bandwidth and the time width. So basically, the pilots were for example, here the ZC sequences, they occupy only very small portion of the frequency time resources. But if imagine that you can utilize all the resources, then you'll end up with a huge ISNR gain. Okay.
Right. Thank you very much. I guess there will be a final question. So I see that all the analysis here are based on ambiguity functions. What about other performance metrics, for example, like CILB or ZZB? Have you ever considered this kind of analysis?
For CRB, I don't think it is a proper metric here, because we are considering multi-target, detection here. Okay, but CRB, it is only used for single targets, or for the case that you have well separated multiple targets. That is because CRB is not able to reflect the ambiguity effect of the multi-target ranging. So here the ambiguity effect is that if you have multiple targets, they will interfere with each other, right? But for CRB, it essentially assume that these targets, they are not interfere with each other. Okay.
Right.
So CRB in this case, for the multi-target case, will be a very, very loose bound. So we are not analyzing that previously. And for the ZZB, the problem is that it can reflect the ambiguity effect, but it has a very intractable mathematical expression, and it's very difficult to analyze. So the ambiguity function is in between these two, metrics. I think it is more realistic. It reflects the practical ambiguity effect of multiple target detection, and it is mathematical tractable. So that is
Right.
why we choose ambiguity function. Okay.
Thank you very much for the answers. I think that's pretty much all the questions we had so far. And please join me to thank you again, Professor Liu, for this wonderful presentation. And if you have further questions, you can send him an email in the future to discuss offline. Okay, thank you again.
Okay, thank you, Shanya.
Okay, our next presentation is going to be given by Professor Stefano Buzzi from Italy, and the stage is yours. Thank you.
Okay, good morning. Can you hear me?
Yes.
Okay. Thank you very much for this kind invitation for this event. And okay, I'm going to share my screen. Okay, so good morning again. And okay, my presentation will be this time not about Isaac, but just about a novel modulation for in the delay-Doppler domain. Basically, this modulation, we have named it Doppler resilient universal filtered multicarrier, and it comes from a merging of OTFS principles with the UFMC principles. Okay, first of all, before starting, just let me provide some thanking. First of all, this work has been developed in the framework of a cooperation agreement between CNIT, that is the consortium of Italian universities, and my own university. University of Cassino is affiliated with CNIT, so I'm a member of CNIT as well, and between CNIT and Huawei. This is a joint work with my colleague Carmen D'Andrea at the University of Cassino here, and also with colleagues from Huawei, in particular Maria Fresia and Xiaofeng Wu. And the material that I'm going to present is taken by a conference paper that we presented a couple of years ago, basically in June 2023, at the USCNC conference, but also comes from a material that has not yet been published. In particular, there is a submitted patent. Last fall, we submitted the patent with Huawei, of course, and there is also a journal paper that is in preparation, and that contains basically the material of the patent, and is going to appear on arXiv in about 1 month. So there will be material that is already published, and some other material not yet published. This is the first time that I'm disclosing, and but soon it will appear with all the details on arXiv. Okay, so here is the talk outline. There will be a brief introduction and motivation of our work. Then I will briefly review about UFMC and OTFS, that are the two modulations that merged together can give the principles for designing the Doppler resilient UFMC modulation. Then there will be a performance analysis in terms of SINR for the case of known CSI. And then we will address the problems of data detection and also channel estimation. And in particular, we will propose a new pilot scheme for this type of modulation that permits very good performance regarding channel estimation. And finally, there will be the conclusions. Okay, regarding the introduction, let's say that OFDM, as you know, is a very good waveform. By the way, Fan just showed that it has also some optimality properties from the point of view of Isaac. So it's basically the modulation schemes that, as you know, is adopted in 5G systems, in many more other systems, like, for instance, Wi-Fi, ADSL, and so on. It has very good performance on frequency selective channels, because basically we are able to remove all the intersymbol interference thanks to the use of the cyclic prefix. But on the other hand, I mean, there are also some drawbacks. For instance, the fact that it is not a very good modulation when we are in scenarios with high Doppler shifts. In particular, in this case, the orthogonality among subcarriers gets destroyed. So there is again intercarrier interference, and on top of this also channel estimation becomes more difficult, because the usual pilot schemes that are used in OFDM under frequency selective but static channels do not work very well. So you have a double effects. I mean, there is both intercarrier interference and both difficulty in acquiring good channel estimates. On the other hand, just for this reason, some years ago was proposed the OTFS modulation, and one thing to say is that OTFS is a multi-symbol transmission scheme. So while in OFDM you are going to transmit just a vector, in OTFS you are transmitting a matrix. So you have not only you are not only transmitting on multiple subcarriers, but you are also transmitting on multiple time intervals. So this makes also the processing, the block that you receive, longer, because it's a matrix, it's no longer a vector, and this also has an effect on the receiver complexity. And OTFS also has large out-of-band emissions, just like OFDM. And do you need, when there is this modulation is used, there is a need for null guard subcarriers. So basically, at the edge of the spectrum, you cannot load the subcarriers. On the other hand, years ago, this fact that you must have zero loaded subcarriers at the edge of the spectrum was pointed out as a drawback for OFDM. And so there was a new modulation introduced at the universal filtered multicarrier. This was about 10 years ago. That was one of the modulations that was able to reduce these out-of-band emissions. Okay, what we are going to do today is to talk about Doppler resilient UFMC. That is a novel waveform that merges together concepts from OTFS and UFMC to achieve both good performance in Doppler environments, in high mobility environments, and also good out-of-band emission containment. Okay, just to give a first recap, of the UFMC modulation. I have here this slide. Basically, how does UFMC works? It's just like quite similar to OFDM, with the difference is that the subcarriers are grouped together in subbands. So I take a group of adjacent subcarriers. They are taken together, and before being transmitted, they are filtered in order to reduce their bandwidth. Okay, so basically here there is the scheme. So S is the vector to be transmitted, and while in a normal OFDM, in a usual OFDM modulation, this vector is undergoes a IFFT transformation. Here it is divided in several blocks. For instance, S0 that contains the first bunch of subcarriers, then S1 that will contain the next bunch of subcarrier, and so on until the last block that contains the last group of subcarriers. All of these subcarriers are subject to a k-dimensional IFFT, where k is the size of the original block here. And then there is a filtering here in order to, so there is a FIR filter, so a filtering in the digital domain that reduce the bandwidth occupation of the IFFT, and then all of these are summed together, and then there is the usual processing that does not use the cyclic prefix. So there is just digital transmission, conversion to the time continuous domain, shaping filter, conversion to radio frequency, amplification, and transmission. This modulation trades off interference for better spectral efficiency. Why interference? Because of course there is no more the cyclic prefix, and also this subband filtering here basically destroys orthogonality between the subcarriers. Just to give you an idea of the spectral the behavior in the frequency domain of this modulation, you see here the spectrum of 6 different UFMC resource blocks with 12 subcarriers each. that carry random QPSK signals. Okay, so this is what you expect to see in the frequency domain. And in this other plot here, there is the comparison between the OFDM, that is the black lines, and the UFMC, that is the green. Okay, and you see that there is a very significant reduction in the bandwidth occupancy. Okay, now so UFMC is very good at transmitting, reducing out-of-band emission, but when you have a linear time variant channel, just like this, okay, that is modeled here as a discrete number of path P, and then we have a complex gain coefficient associated to the path number P. Tau P is the delay, and now here we have also this Doppler shift nu of P. Okay, now if nu of P is 0, UFMC has very good performance. But if nu of P is not 0, so we have some Doppler shifts, what happens is that we have a very huge degradation of the performance. In particular, in this plot here, we compare the UFMC with the OFDM in terms of spectral efficiency as a function of signal-to-noise ratio. And you can see that, okay, for the case of no Doppler spread, so basically static channel, and for the case of channel where the mobile can have a uniformly distributed speed in between between 0 and 100 kilometers per hour, up to 0 and 500 kilometers per hour, and you see how there is this degradation of the spectral efficiency. By the way, you see also here that thanks to the better spectral containment, UFMC indeed needs less a lower number of waveforms set to 0, subcarriers set to 0. So in the end, we get much better spectral efficiency. So this plot basically motivates us to do some further investigation in order to see if UFMC can have good performance also with high Doppler spread. So the objective is to improve performance in the presence of Doppler shifts, possibly with reduced out-of-band emissions. Years ago, there was the introduction of this orthogonal time-frequency space modulation. This was made by researchers from Cohere Technologies, that is a company from the Silicon Valley in the US. Basically, their idea was to consider the data generate the data to be transmitted in the Delay-Doppler domain, because if you have a standard if you have the standard time varying impulse response of the channel like this, and if you perform here a Fourier transform with respect to t, you get something like this. So you get an expression that contains basically Q delta, both in the delay and in the Doppler domain. So basically, you see that a time-varying channel, when considered in the delay-Doppler domain, it can be seen as a very sparse channel, and this can be exploited by the modulation by the OTFS in order to get good, to reduce basically at the minimum the distortion introduced by a time varying and frequency selective fading channel. So that was the breakthrough, basically, to consider transmission of data in this domain, where the channel distortion should be, the less harmful possible. Okay, so this is the scheme of an OTFS modulator. I will go fast, but it can be seen basically as a typical OFDM modulator, where before the OFDM modulator, this is cascaded with a two-dimensional IFFT that is called inverse symplectic FFT, that is nothing but a two-dimensional IFFT. In particular, we can provide a little bit of math. We say that XDD is of size k by n, where k is the number of subcarriers and n is the number of consecutive symbols that we consider, that contains the information symbol in the Delay-Doppler domain. XFT is based on the two-dimensional IFFT, inverse FFT of the data. So basically you have to pre-multiply and post-multiply by FFT matrices. And S instead is the signal that undergoes the IFFT of the OFDM modulator. In this case, we consider an oversampled IFFT in order to simulate the multicarrier transmission in the digital domain. And at the receiver, basically, there is the processing that is usually done by the OFDM modulator, and then this symplectic fast Fourier transform that basically provides the inversion of this block here. And in the end, we end up with this YDD, the data received in the delay-Doppler domain, and if we vectorize this expression, we end up with a linear model that relates the transmitted symbol here, that are the symbol contained in this matrix that here we call by X, related to the ones that are received by this very simple MIMO model, where V is the additive Gaussian noise and psi is a matrix that takes into account all of the processing. Ideally, we would like to have this be a diagonal matrix, but actually it is not. But in some particular conditions, it's diagonally dominant, and this can help a lot the detection. Okay, now we are ready to introduce the Doppler resilient UFMC modulation that basically mimics the scheme of this OTFS. While here in OTFS we had just an OFDM modulator and OFDM demodulator that was preceded by an inverse symplectic FFT transform, and then in the end we put at the end of the receiver chain a symplectic fast Fourier transform block. Here we do the same, but with the only difference that in place of the OFDM modulator, we put an UFMC modulator. Okay, so we are going to analyze this scheme. So we take this UFMC modulator and demodulator, and we put at the beginning and at the end these two schemes, the ISFFT and the SFFT, and see what happens when we study this type of new modulation that comes from this scheme. Okay, basically remember that this is the UFMC modulator. So SI was just the signal and the output that I mean, here you have several of these signals, because remember, this is the contribution from the first subband that is filtered. This is then there is the second subband, and B is the last subband, and all of these subband are summed together. Basically, what you have here can be expressed like this. So you have the data that is the input that is pre-multiplied by PI, that is a selection matrix that selects the ith subband. Then you have the oversampled IFFT over K point, and then GI is the convolution matrix that simulates the FIR filter, the finite impulse response filter that performs subband filtering. So all of this to say that basically in the end, all of the processing of the UFMC can be described by a matrix that pre-multiplies the data that is the input here. And this is very important because we will exploit this expression later when we will introduce the pilot design for channel estimation. Also in this case, okay, one thing to say is that, of course, this scheme introduces, due to the presence of the subband filtering, we have that the K subcarriers actually are enlarged. So we have interference already among the blocks already at the transmitter. Then there will be further interference introduced by the channel. Okay, so this is just to say that this scheme trades spectral efficiency and good performance with complexity. Because we have a lot of interference that we have to take care of. And also in this case, likely we end up with a linear model. So the data transmitted, the symbol transmitted and the received symbols are related by relation like this. Just to give a first idea of what can be the performance of this, we can focus on spectral containment. And here we plot the power spectral density of the OTFS and DR-UFMC transmitted signals in a situation with 128 subcarriers, 16 symbols, consecutive symbols. This is the subcarrier spacing over sampling factor. And okay, you see here the same figure where we have assumed that we want to take the out-of-band emission below 30 dB with respect to the maximum value. And you see here that in case of OTFS, you need to put to 0 a certain number of subcarriers that are given by here and here. Here, instead, the number of subcarriers that are needed to put to 0 are much lower. Or in particular, I mean, this line here has a length that is less than this line here. So you get less bandwidth occupancy. So there is a reduced number of subcarriers that you can put to 0. Okay, based on this, we can compute the spectral efficiency that we compute like the log in base 2 of 1 plus the SNR that we get on every subcarrier, multiplied by a pre-log factor that takes into account the loss in spectral efficiency introduced by the number of subcarriers that you have to put to 0. And if you use the standard linear MMSE processing of the receiver, you can come up with a very simple expression of the SNR that can let us make some initial comparison in terms of spectral efficiency. In particular, we compare four different modulations. In particular, we compare OTFS with full linear MMSE processing. Then we compare our proposed scheme, the Doppler resilient UFMC scheme, with full linear MMSE processing. And then for benchmarking purposes, we also compare OFDM, put OFDM into the scene. In particular, if you take into account, you do all the math with the time varying channel, it is easy to realize that also for OFDM, we can end up with a simple MIMO linear model of the type that was shown for OTFS and DR-UFMC. So we have this model Y equal to a mixed matrix times the data plus the noise. So we can apply the full linear MMSE processing, or also we can apply the processing that we have with the standard one-tap frequency domain equalization that we know is optimal, performs very well if the channel is static. Okay, it's not varying time. So we propose we compare these four techniques for two cases. A case where we have 50 kilometers per hour, so maximum speed, and the other is 500 kilometers per hour. Okay. This expression reports the net signal to interference plus noise ratio per subcarrier and per symbol in the dB for these four considered modulations as a function of signal to noise ratio. Okay. And okay, if you look at this, so if you look at the SNR, there are some interesting things to say. First of all, you see that OFDM actually performs quite well in the sense that it's not really, I mean, it's common wisdom says that OFDM does not perform well in time varying environment. Actually, it does not perform well if we use it with frequency domain, single tap frequency domain processing. But if we consider a little bit more involved and more advanced receiver schemes, we can have good performance. Then, so actually here it is the best. Then we have the OTFS. Then here we have the DR-UFMC, and then we see that OFDM with frequency domain equalization actually performs not very well. And this actually confirms the fact that if we do just frequency domain equalization, we don't have good performance with OFDM. So from the point of view of the SNR, the best is OFDM, and DR-UFMC is in the third position. But if we consider the spectral efficiency, taking into account not the SNR per subcarrier, but taking also into account the fact that you have to put to zero some carriers at the edge of the spectrum to meet the out-of-band requirements, in the end, what happens is that the best performance actually is the DR-UFMC. And then we see that the OFDM and the OTFS has approximately the same performance, while on the other end, the OFDM with frequency domain equalization does not offer very good performance, and in the end, we have a floor due to the interference, a lot of interference that is not compensated by advanced receiver schemes. Okay, so the comments that we can offer so far is that in terms of net signal to interference plus noise ratio, OFDM with full processing, OTFS and DR-UFMC achieve approximately the same performance. That was the first plot that we showed, while OFDM with one tap FDE, frequency domain equalization, exhibits a heavy performance degradation, especially for large values of the maximum speed of the mobile user that is considered. And OTFS, DR-UFMC, and OFDM with full processing are almost insensitive to the value of the maximum speed, and indeed the results for 50 kilometers per hour or 500 kilometers per hour were almost the same. Finally, if we focus on spectral efficiency instead, we have a very good clearly evident superiority of the DR-UFMC with respect to the other competing alternatives. In particular, you see here the plot, the red is the DR-UFMC that has the best performance. And you see here also the insensitivity to the maximum velocity, okay? From 500 to 1500, degradation is very, very limited. Okay, so far so good. But what we have presented so far is not take into account the problem of detecting designing the detector. We just showed SNR values based on LMMSC linear processing in the receiver, and we did not consider as well channel estimation. Okay, I will first consider the problem of data detection. Data detection is challenging because the matrix, even if we have a linear model, the matrix psi is not diagonal at all, especially for both for OTFS, but even more for DR-UFMC. And so this implies that linear detector, and we will see the performance of these detectors, just like zero forcing and linear MMSC, do not work properly, and nonlinear processing is needed. And so we need a nonlinear processing. We don't need to invent anything here because this is just a standard linear MIMO detection problem, and we have hundreds of papers that have dealt with the problem of detecting data symbols when we have a model like this. I report here also some relevant references here that are used that have addressed these problems, and in particular we show results just to give you an idea for several schemes. I anticipate that the best schemes will be this one, the nonlinear SIG, that is the one that we will use for further derivations. Okay, let's see what we report. Okay, we first of all, our benchmark is the linear MMSC receiver, the usual one. This is linear. Then we have also an approximation of this receiver that is based on the Gauss-Seidel approximation to the MMSC detector. Basically, this comes from the fact that if we don't want to afford the complexity of this detector that requires a channel matrix inversion, there are ways to approximate the inverse with the Gauss-Seidel iterations. That is a method for matrix algebra, and so we have an approximation of the MMSC. Both these algorithms will not work very well, I anticipate. Then we have message passing algorithms that basically were introduced in references 2 and 3. And also these are nonlinear schemes, have better performance compared to these two, but not that much. And then we have two algorithms that are proposed by ourselves, but basically nothing new. I mean, it's a concept that are around, that have been around for a while. And we will see that this scheme, as was said, the 5 is the best performing one. Okay, I skip the the explanation of the message passing because it's quite involved, and also you can refer to this reference here. But I spend a little bit more time about this nonlinear LMMSC based serial interference cancellation. So basically, what is the idea here? The idea here is to start with the, okay, we have several symbols to detect. We have a mixing matrix. What do? We start by detecting the symbol with the highest SNR. So we find the symbol with the highest SNR if we apply, in the case in which we apply a linear MMSC estimate, and decode this symbol with the linear MMSC technique. So we start by decoding with linear MMSC the symbol that has the highest SNR. So it is the one that is supposed to be decoded with the lowest symbol error rate. Then we quantize it, and then we what do? We update the observable by subtracting the contribution of this symbol by the observable. Okay, so we take the observable and subtract the contribution from this strongest symbol, okay, the one that had the SNR largest, okay, and then we repeat. So at this point we compute the SNR for all the remaining symbols, and again we detect with the linear MMSC detector that now will be a new LMMSC detector because it is computed on a different covariance matrix. So we detect the next symbol with the largest SNR, and then we detect it, quantize it, and then subtract its contribution from the data. And we go on with this strategy. So every time we detect the largest, the symbol with the largest SNR, so the one that has the highest likelihood of being correctly decoded, and then we subtract it from the observable. And this is the way in which we detect all the data. And just one comment: notice that every time that we do it, every time that we remove the contribution from one symbol, we have a new observable, and we have a new covariance matrix, but we don't need to compute its inverse by scratch again, but we can do it with reduced complexity thanks to it's a rank 1 update. So we do the matrix inversion lemma. We use the matrix inversion lemma. Okay. Then there is this heuristic sphere decoding. I give you a very simple explanation. Suppose that at some point we detect a symbol with a linear MMSC scheme. Then we use the maximum likelihood, the minimum distance receiver decoding rule, not considering all of the possible realization of X of the transmitted vector, but just considering the symbols that are around. Okay, so this is just an approximate way, a reduced complexity way of approximating this maximum likelihood, minimum Euclidean distance optimum detector. Okay, I'm ready to present some performance results for all of these detectors, and basically these are the results. You see here that the nonlinear SIG, that is the purple, is the best one both for the OTFS and the Doppler resilient UFMC schemes, so it's the best one. The worst, of course, are the MMSC, that is the red, and its Gauss-Seidel approximation, that, of course, being an approximation of the MMSC, performs even worse. We plot here with the green and the black, actually the worst in this case was the message passing, the modified message passing. We weren't actually able to have it working. And you see here the one based on the heuristic sphere decoding, that is this curve here, that is not that bad. But in any case, I mean, in both cases, the nonlinear SIG appears to be the best performing scheme. And so we show here the performance of only this detector for the 4 considered modulation schemes. For OFDM with frequency domain equalization, for OFDM with full processing, full LMMC processing, and for the OTFS and the DR-UFMC. And again, the results here show that DR-UFMC behaves very well because it has a performance that is quite close, comparable actually to the one of the OTFS. Okay, now we are so far, these are data detection results that have been presented under the assumption of perfect channel state information. Okay, we are now ready to address the problem of channel estimation. Now for OTFS channel estimation, there are several schemes proposed in the literature, but the most successful approach is just to consider a pilot scheme, a pilot that is embedded in the Delay-Doppler domain. So basically, this is the Delay-Doppler grid where all the data should be filled, and it is assumed that in this blue part contains the data. Then here there is put an high frequency, high energy symbol, and these green are all guard symbols that are put to 0. So basically, we consider a tile at the center of the Delay-Doppler grid. It is a tile that has all zero elements except the element in the center that contains a high energy pulse. This is just a drawing. But this instead is taken from MATLAB, and so this is for the case where we don't consider the data, so we just put the high energy pilot at the center. This is what we get as what we transmit in the Delay-Doppler domain, and this is what we receive in the Delay-Doppler domain. Okay, so this is the OTFS. Basically, the peak here, we should have several peaks, and every peak should correspond to a path of the channel, and the location of where this peak is located gives you an idea of the delay and of the Doppler that is associated to that path. Now, in order to really have estimates of these paths, what is done? Maximum likelihood channel estimation is performed with an exhaustive search over all the possible values of channel path gains, delays, and Doppler frequencies. And this exhaustive search, however, is complex because we have to look for in a multi-dimensional domain for the values of the delay, of the channel gain, and of the Doppler frequency that maximize the likelihood of the data that is received. So we have suboptimal search procedures that are employed. And as a further improvement, we also propose an iterative procedure that permits using the decoded data as a virtual pilot sequence. So what is the idea that we do? It's quite very simple. Once we receive the data, we do channel estimation. Then based on the estimate of the channel, we detect the data. Now that the data has been detected, so all the data in the Delay-Doppler grid, we feed back this data to the channel estimator, and the channel estimator can perform again the estimate of the channel, assuming that now all the data in the Delay-Doppler spread are a virtual pilot sequence. So basically, what do? We use the decoded data, assuming that the decisions that have been taken on the data are correct. So we use the decoded data as known symbols. So basically, thanks to the fact that we have decoded the data, we perform again channel estimation, assuming every if they were part of the pilot. Okay. And you see here that we plot here the normalized mean square error in the estimation of the data symbols based on the every iteration. In this plot here, we have the normalized mean square error. For the case of perfect channel state information is the blue line. And this is the performance that we get if we do not take this scheme. But if we assume this scheme, you see that after one iteration, two iteration, three iteration, actually the results improve a lot. So this is an effective way to be able to get even better performance in the decoding of the data when you have a challenging situation with a lot of interference and a strongly non-diagonal matrix, mixing matrix like in this case. Okay, now we are almost over. Time is almost over, a few minutes, and I'm going to finish. I'm ready to present the channel estimation procedure with the DR-UFMC. Now, if we assume that we proceed like we do in OTFS, we have a problem. And what is the problem? Actually, the problem is represented here. Due to if we just put a one high energy symbol at the center of the delay-Doppler grid. And we see actually that what we receive in the delay-Doppler domain is not this that we receive in the OTFS case, but we receive something like this. So basically, there is a spreading of this pilot sequence over all the in many parts of the delay and the Doppler domain, because we have that the subband filtering basically spreads, introduces some convolution effects in the system, and basically this pilot symbol is spread all over the delay-Doppler grid, so there will be a lot of superposition with the data, and so this makes that the performance of the channel estimation with a pilot like this is not really very good. So what do we do? Basically, what we would like to have is that here I'm reporting the scheme of the OTFS transceiver and UFMC transceiver. In order to be able to get at the receiver a pattern just like this, like the one of the OTFS, when we use DR-UFMC, we need to ensure that the signal that we are going to transmit on the channel is the same like the one that we have with OTFS. So the idea is to introduce a pre-distortion of the pilot. In particular, we impose this equation. If you see here, this is the signal that we are going to transmit in the case of the OTFS, and this is the delay Doppler, the matrix that contains all 0 and just a 1 in a high energy symbol in the position where we transmit the pilot. So this is what we transmit in the OTFS case. And this is what we transmit in the UFMC case, where P tilde UFMC is, of course, the processing introduced by the UFMC. Remember that at the beginning of this talk, I said, look, the UFMC processing is just the pre-multiplication for a proper matrix, okay? Now, if we want to have the same type of distortion at the receiver, we need to ensure that also the transmitted symbols is the same. So we equate these two terms, okay? So this is what we transmit for the OTFS, and this is what we transmit for the DR-UFMC. And from this relation, now we can treat this as an equation where this matrix is an unknown. So we end up with this expression that basically provides to us an expression of how is to be done the pilot in the DR-UFMC in order to avoid this effect here. And actually, if we use this pilot, basically this is the pilot. So it contains not only data at the center, but also proper values in other points. If we do this, you see actually that we get at the receiver a pattern that is very similar to the one that we get in the case of OTFS. So thanks to this pre-distortion of the pilot, we are able to get a pattern at the receiver that is very similar to the OTFS. And so the channel estimation techniques that are used for OTFS with very few modifications can be used also for DR-UFMC. Okay, this is the same for the case where we also include the data. So this is what we are going, the delay-Doppler domain, the matrix that we transmit in delay-Doppler domain for OTFS. So here there is the data, here there is the empty tile, and here there is the high energy pilot. This is what we get in the case of OTFS. For DR-UFMC, this is what we are going to transmit. So here there is the pilot here, but also you see here, there are also the pilots are there, overlapped with the data. And when we transmit this signal, we see that here we are able to get a pattern that is very similar to this one. And indeed, we will be able to do channel estimation and have good detection. So to finish my last 2 slides, in this plot, what I'm going to report? I'm going to report the normalized mean square error in the estimation of the data symbols, where as a function of the signal to noise ratio. For what? For the DR-UFMC modulation. And we have 3 plots, 3 lines, basically. The blue line, the benchmark, is the performance if we know perfectly the channel, okay? The the green, sorry, is the one if we use the OTFS-like pilot, so we don't do the pre-distortion. While finally, the red one is the performance that we are able to get when we do that type of pre-distortion. And you see that we get a performance that is pretty close to the case of perfect channel state information. So to conclude, delay-Doppler communications are an interesting and popular research topic, and because you can have very good performance in the presence of time-varying channels, notably in the presence of high Doppler shifts. And we have presented this DR-UFMC that merges together OTFS and UFMC. And we have considered the problem of modulation design, detection, and also channel estimation. The results regarding the pilot and the channel estimation are not yet public. I mean, this is the first time that I'm disclosing them, and but we soon presented in a paper on arXiv, hopefully in a few weeks. And currently, we are also working on the extension of this work that I have just presented to the case of multiple antennas, and in the case where we have massive MIMO with multiple users, because basically all the presentation was for the one antenna case. Okay, so we had the transmitter with one antenna and the receiver with one antenna, but now we are considering what happens if we do the multiplexing of several users that are using this type of modulation, multiplexing in the space domain to see if with an antenna array we are able to separate them. And again, this introduces a new form of estimation, because before the beamforming, we have to estimate the channel. In this case, we have multiple users transmitting UFMC that are simultaneously received. So there are some other challenges associated with this type, with this case of multi-user processing. Okay, that concludes my talk, and thank you very much for the attention, and I'm open for questions, if any.
Thank you, Professor Stefano. That's a very, very good and a very interesting topic, to be honest. This type of waveform has not been published before, and we are very honored to be the first audience listening to these details. There are several questions. Actually, it's also my personal interest. I'm really curious about the extension to MIMO case, as you have already briefly mentioned. Well, do you think the extension of the current waveform to MIMO will still based on subcarrier-based precoding, like people in OFT understood?
Okay, it could be basically, yeah, that's one technique. So you mentioned, you say, okay, we can use different subcarriers in order to separate the users. Okay, at least at the beginning. Yes, it could be, because at the beginning, I mean, if you think of a massive MIMO system, in the beginning, you have several users that start transmitting simultaneously the pilot sequence. Once the base station has decoded estimated the channels, then you can do beamforming, and in that case you are able to separate them in the space domain. But before you do this, you cannot do any type of separation in the space domain. So that's one thing, that's one possibility. The other possibility is using pilot sequences, the tile of the pilot allocated in different portions of the time frequency, the delay Doppler grid, in order that the pilot from one user doesn't overlap and makes too much interference with the pilot from other users. Definitely.
Yes, thank you for the answers. Another question I'm curious about is actually about the filter design. We are mentioning that there is a drawback for OTFS, that it has a very strong out-of-band emission. And there are actually in the literature, there are people proposing using different type of filters, either in delay-Doppler domain or in time domain to mitigate this out-of-band. Have you comparing the new waveform with OTFS, particularly with the filtered OTFS case?
No, this has not yet been done, and this is an interesting suggestion. Actually, I also saw a paper it was a period in January in an archive by a researcher working on this field, where he proposed this globally filtered OTFS that basically is very strictly related to what I do. And so yes, that's these new versions of OTFS is something that is to be considered. But in any case, one thing that I see in all of these solutions is that the detection is very complicated. So one should also work on ways to efficiently estimate the channel and then do the decoding. Because especially if we think of the downlink, that can be really a problem, because of course in the mobile user we don't have too much computational power, so that is one thing also to take into account.
Yes. Okay. There's another question related to what you just mentioned. In the detection problem, especially in the OTFS literature, people are concerning about the so-called fractional delay and Doppler case. And I wonder, since the new waveform you have also proposed using several filters in the time frequency domain, but eventually you are detecting the symbols in the delay Doppler domain, do you think the fractional delay Doppler issue will also affect the performance of this newly proposed?
Yes, because it affects the channel estimation performance. Definitely, that is a problem. One thing that we are not mentioning is that probably machine learning could be useful here. So basically, I mean, if we are able to, because suppose that OTFS gets standardized, you have that the number of at that point you will have a numerology, okay? So you will know in advance what is the number of subcarriers and what is the number of symbols. So in this case, you can offline train some machine learning detector for that type of numerology. Because one thing of machine learning, okay, I have this algorithm that works, but what happens if I have one more subcarrier or one more? I mean, it's just a customized solution that works for that type of for that size of the matrices. If the waveform gets standardized so that we have just a finite number of possible numerology, then maybe in that case, these in a neural network could do the job. This is something that should be looked into.
Yes, that's a very interesting topic. The final question I have received is about the pre-distortion method you propose for the channel estimation part. It seems like for me that you need several more pilot symbols in the delay Doppler domain, such that you can have this pre-distorted case.
Okay, let me share again the screen just for a few seconds. And okay, you see the presentation?
Yes.
Okay, actually, this is not the case, because I mean, this is the better. Okay, here, as I was saying, we are okay. This is a symbol that is this symbol here is used by a pilot, but here we are superimposing also the data. So we are transmitting both. So it's
Right,
just
right.
the occupation is exactly the same. So because this is the highest energy symbol, so we put here the tile, but here there is not, here we let's say the redundancy is the same, just like OTFS, because here we
Right.
make a superposition of both the pilot and the data.
Right. That's a good point. I assume there is also somehow a way to truncate the power, right? Otherwise, you are doing pre-cancellation will potentially increase the transmitted power somehow, right?
Yeah, actually, what happens is that the power is not that much, because since I mean,
Okay.
we have done the of course, in order to make the comparison fair, we are assuming that the pilot is sent with the same power. So in this case, all the power of the pilot is concentrated here. In this case, the power of the pilot instead is spread over all of these symbols. So basically, what happens is that this peak here is lower than in this case, and also here there is not so much power, basically.
I see. That's very good.
Okay.
Thank you very much for the
But as you mentioned, probably we have to control that the overall power given by the data plus the pilot is not that much. Okay, this is a check that we have to do. Even though I expect to be not that much, because even here graphically, I mean, this should be less powerful than this. That in turn is less powerful than this one. So there should be no problem. But this is one important thing to check. So this is a very, very good question. Thank you.
Thank you very much. Yes, that's great. Thank you again for the answering. That's a very great. It's quite clear presentation, and it's a very interesting new topic. Okay, and I think this is pretty much all we are having for today's presentation. And thank you again for joining us today, Professor.
Thank you very much. Thank you very much. Thank you everyone for the invitation, in particular for you for organizing all of this. Thank you very much.
It's a pleasure. Thank you.
And also greetings to Fan. Hi, Fan. It was nice to see you.
Nice to see you again. Yeah.
Yes.
Okay. Thank you very much. Bye.
Thank you. Thank you again for joining us. Yes.
Bye.
Thank you very much.
Mm-hmm.
I think, yeah, since we do not have any other questions, we can conclude this meeting. I would just like to add for all participants some details in the message box, so they can check on the C forum, and they can receive their certificates. And to add that the webinar will be available early as possible also at the C forum as a video, so everyone can check and subscribe to check. And one more thing, for all participants, since we are looking forward to receive some feedback to improve our future webinars, I also attached the link to fulfill our satisfaction survey. So please check these links, and you can receive your certificate. And I just want to thank all the participants and our speakers, and of course our chair, Dr. Shangyang Li, for this very successful webinar. Okay, does anyone else have something to add, or we can conclude this webinar?
That's very good.
Okay, thank you very much. We can finish now. Okay.
Bye.